Okay, so I'll just make it bigger. So our topic for today, as I have said, is about digital to analog conversions and analog to digital conversions. And in modern life, electronic equipment is frequently used in different fields such as communication, transportation, entertainment, and others. And a very important element in electronic equipment is the analog to digital converter and digital to analog converter. Why? What is the reason behind that? Because most real world signals are analog. Okay? So when I try to speak this morning, as you hear my voice, actually the voice that you are hearing from me, they are all coming from my mouth, right? And they are all analog signals. However, they are picked up or they are being received by my microphone, which in turn my microphone is connected to my laptop. Okay? And this microphone, as you can see from the background, you may hear some roosters. So they are also analog signals. Okay? So that's one of examples that we can see in the real world signals wherein we can hear analog sounds coming from people, coming from animals, and we can say that these two interfaces, the ADC and the DAC, they allow digital electronic equipment to process the analog signals. Now, as you can see from the example here, the audio signal processing, which is in the above example here, the analog to digital converter, as I have said, when you hear my voice, it's being collected by the audio input equipment, which is the microphone, okay? And it is being converted into digital signal, okay? That is actually, I'm using a, inside my laptop, it is being processed, converted into digital signal. So the analog signal coming from my mouth will be converted into digital signal, okay? And then using the application, which is, we're using the application from the canvas, which is big blue button, you are now hearing it converted to you, and actually when you hear it, it is turned back into an analog signal as the output in your speaker. If you have, for example, a headset also, or coming from the speaker of your computers. So the computer, sometimes they add sound effect such as echo, and also they can adjust the tempo and pitch of the music or sounds. Okay, so if you have some effects there, for example, I'm using an application called Crisp. The Crisp is a actually it's a plug-in, okay, from my browser. I use it to filter the noise coming outside, okay, so that it will not be too loud for you to hear everything in my background. So the computer does that, okay? And digital to analog converters converts the process digital signal back. As I have said, when it is being converted into a digital signal, it is converted back to analog signal for the output. Okay? So that's a typical scenario where both the analog to digital converter and digital to analog converters are frequently used. Okay? Now, aside from that, we have here the concept of what we call sample and hold circuits. And these sample and hold circuits are very important part of analog to digital converters, because they help uh, in the accuracy of the conversion of the analog signals to digital signals. No? From the illustration, we have here an analog input, okay, and it is sampled. Okay, it is sampled. I will explain later what sampling means. Okay, and from the last figure, you will see the analog was converted into, or hold, it is sampled and hold. Okay, so this is the illustration of being sampled, where the signal, the analog signal is sampled, and then it is being hold here. Okay, so a sample and hold circuit, represented as SH circuit or SNH circuit, is usually used with an analog to digital converter to sample the input analog signal and hold the sampled signal. So when we say sample, no, when we say sampling the input, actually we are capturing, or we are taking the voltage of a continuously varying analog signal. And when we say hold, we are actually okay, or we are actually locking or freezing the value at a constant level for a specified minimum period of time. So definitely, to be able to do this, we need a circuit, no, an electronic circuit to do this, and that is what we call the sample and hold circuit. Okay, so sample and hold circuits and related peak detectors are the elementary analog memory devices, no, and they are typically used in analog to digital converters to eliminate variations. As you can see from here, there are varied signals coming from the analog signal. Okay, so to eliminate this, we use sample and hold circuits so that it can process, and it can actually we can actually eliminate variations in the input signal that can corrupt the conversion process. Okay, and they are also used in many examples, such as, for example, in electronic industry or music industry, for instance, to impart somehow a random quality, for example, to successively play some notes or some tones. Okay, so those are the things that we can get from sample and hold circuit, no? So you can see from the analog input, okay, an analog signal here, no? So actually, analog signal can be defined as any continuous signal. So as you can see here, it's a continuous signal for which the time, okay, this time varying feature of the signal is a representation of some other time varying quantity. Like for example, here we have the amplitude, no? So there definitely it is analogous to another time varying signal. Alright? So in terms of the sample and hold circuit, the analog signal is sampled, no? As I have said, when we say sample or sampling, we are actually capturing or taking the signal, okay, the voltage of a continuously varying signal. Okay, so how much time do we need, do the circuit need to do that, no? It says here that it is usually in the range of 10 microseconds to 1 microsecond. Okay, and after this, after the sampling, the sampled value is hold or freeze until the arrival of the next input signal to be sampled. Okay? The duration for holding the sample will be usually between few milliseconds to few seconds. And the image here that you can see is a simple block diagram of a typical sample and hold circuit. No? So we have an input voltage. Therefore, if we have an input voltage here, we have a varying input or analog signal, and then we have the sample and hold circuit here, and we have the output voltage. Okay, so this is an example, just a block diagram. Now, what are the operations of sample and hold function? No? For example, we have here the sampling. Okay, so we have two functions actually, right? Sampling and holding. So sampling is the process, no, of taking a sufficient number of discrete values. Okay, so as I have said, sampling is about capturing or taking the voltage of a continuously varying analog signal. Okay, that's one of the functions of the sample and hold function. So we are actually taking a sufficient number of discrete values at points on a waveform, so that will define the shape of the waveform, and actually it converts an analog signal into a series of impulses, each representing the amplitude of the signal at a given instant in time. So we can see from the example here, we have the analog input, okay, analog signal, and it goes through the sampling circuit, and this will be the output of the sampling circuit, wherein certain points, discrete values of points, are taken as a waveform. No? So this will be the shape of the waveform, okay, represented by the amplitude of the signal at a given instant of time. For example, every 10 microseconds or every 5 microseconds, we have these points, no, or amplitude. So it says here that the more samples you take, the more accurately you can define a waveform. So it depends on the variations of the time, at a given instant of time. Okay, so this is a sampled variation of input signal, no, given from the analog signal that we have here. Now it says here that before a signal can be sampled, we need to pass it through a low pass filter, no? So dadaan muna siya sa filtering, and we call it the anti-aliasing filter. So the function of this is that we can eliminate harmonic frequencies which are above a certain value as determined by the Nyquist frequency. Okay, so we'll talk about this later. Now the analog signals, except a pure sine wave, contains a spectrum of frequency, no? This is an example of that. Now for a pure sine wave, these frequencies appear in multiples called harmonics. So those are some terms of the analog signal. Okay, now getting back to the definition of sampling. Okay, so it's defined as the process of measuring. As I have said, the simple term for this is actually capturing or getting or taking the voltage of the varying analog signal. Okay, so it's actually, in definition, it is the process of measuring the instantaneous values of a continuous time signal in a discrete form. Okay, and a sample, when we say sample, it's a piece of data taken from the whole data which is continuous in the time domain, no? as in the example here. Okay, so the analog signal was converted in the series of impulses, no, represented by the amplitude. Okay, so now when a source generates an analog signal, and if that has to be digitized, okay, so for example it is converted into ones and zeros, or either high or low, the signal has to be discretized in time. So this discretization of analog signal is called sampling. Okay, so when we try to discretize the analog signal, it's called sampling. Alright? Now the following figures that you can see from here indicates a continuous time signal, x, which is x. Okay, here we have a continuous time signal and a sampled signal called x of s. So here, below here, no? So when x on a continuous signal is multiplied by a periodic impulse train, the sampled signal xs, we can obtain t. Okay, so definitely we have an illustration here of an analog signal which is converted into periods of impulses. Okay, we call this lines, vertical lines, impulses. So actually it's mimicking, no, we are actually capturing the shape of the analog signal. Okay, so this is what we call sampling. Now we also have a term called sampling rate, no? So to be able to discretize the signals, the gap between the samples should be fixed, and that gap can be termed as a sampling period. So for example, if you want to compute for sampling frequency, it is equivalent to the reciprocal of the sampling period. Okay, so 1 over the sampling period, okay, or TS, where TS is the sampling time and F of S or Fs is the sampling frequency. So this is how we can compute that, no? So definitely they are inversely proportional to one another. Okay, now the sampling frequency, as you can see from here, we have the sampling frequency, or Fs, is the reciprocal of the sampling period. This sampling frequency can be simply called as sampling rate, and the sampling rate denotes the number of samples taken per period or for a finite set of values. Now for an analog signal to be reconstructed from the digitized signal, the sampling rate should be highly considered, and the rate of sampling should be such that the data in the message signal should neither be lost nor it should get overlapped. Hence a rate was fixed for this, and that rate was called the Nyquist rate, okay, or the Nyquist frequency. The Nyquist rate here mentioned here, no? Suppose that a signal is band limited with no frequency components higher than W hertz, and that means W will be the highest frequency. Okay, and for such a signal, for effective reproduction of the original signal, the sampling rate should be twice the highest frequency. So you can see from here the sampling frequency should be twice the highest frequency. W is the highest frequency and F of S is the sampling rate, and this rate of sampling is called the Nyquist, or I don't know how to pronounce this. I just call it Nyquist rate or Nyquist rate. Okay, now talking about the anti-aliasing filter. Okay, so before we have the sampling, we need a filter, and it's called the anti-aliasing filter. Actually, it's a low-pass filter that is placed on the input of an analog to digital converter, or ADC. Now, before we understand about anti-aliasing filter, we need to understand what's an alias signal is. Okay, so actually alias signal is produced when the sampling frequency is not at least twice the signal frequency. The Nyquist rate here tells us that the sampling frequency is twice the highest frequency, right? So if we have the sampling frequency is not at least twice the signal frequency, so that's going to be a problem, no? So we have an alias signal if we have that, no? If that is the case, okay, the alias signal is produced when the sampling frequency is not at least twice the signal frequency, and an alias signal has a frequency that is less than the highest frequency in the analog signal being sampled, and therefore falls within the spectrum or frequency band of the input analog signal, causing distortion. So actually the alias signal, we can somehow relate it to some distortion of signals. Okay, so from here, how do we interpret the distortion? So we have a signal here overlapping. Okay, we have an unfiltered analog frequency spectrum here, colored blue, and the pink color that you see here is a sampling frequency spectrum, no? And if those signals will overlap, this shade here, okay, causes an aliasing error. Okay, so the lower frequency components of the sampling waveform become mixed in, they are mixed in with the frequency spectra of the analog waveform, resulting in an aliasing error. Now, to be able to avoid an aliasing error, the filter must at least eliminate all analog frequencies above the minimum frequency in the sampling spectrum. So as an example, you can see here there's no overlap, and here's the filtered analog frequency spectrum. Okay, because we filtered it. When we try to filter it, we try to eliminate the aliasing error here. Okay, so there is no aliasing error here because it's already filtered. Here, there is no filter being used. Okay, so aliasing can be avoided by sufficiently increasing the sampling frequency, but it's usually limited by the performance of the analog to digital converter. Okay, so it happens, no, this overlapping it causes error, no? So you can hear my voice without error, right, without distortions, because of the microphone that I am using. And of course we have some systems that that prevents the distortion from happening. But along the way, sometimes I hear some students, no, when they are actually using the microphone, we can hear some distortions on the signal, no? For example, if the microphone signal is, or if the microphone is having some technical problems, so we can hear some distortions of signals, no? Okay, although we are implementing actually the filtering of the signal. Okay, so I talk to you about the crisp noise cancelling. We call it crisp noise cancelling. Okay, so it's an application actually, and however it's commercialized, so you can actually get a few minutes only to have the crisp, no? But actually it's a good noise cancelling application that with a single button, the crisp removes all background noises for incoming and outgoing calls. And definitely it's a very good application. Okay, so you can download it from the internet if you want. No, especially nowadays that we're actually using online communications or online online conferences for our meetings. Right? So let's proceed. No, now after the sampling operation, we have what we call the holding operation. No? This is the second part of sample and hold function. Okay, so after the filtering and the sampling, so filtering comes first before the sampling, right? So remember that, the precedence, filtering comes first, and then we have the sampling, and then after the sampling, we have the holding operation. So the sampled level must be held constant until the next sample occurs. So this is the function of the holding. And this is necessary or important for the analog to digital converter to have time to process the sampled value. So if we have the example here, we have the analog input, we have the sample signals here, we have some impulses here, and then we have the sample and hold circuit here, and then the sample and hold operation results in a stair step. No, this is it's like a building, no, a drawing of a building, but actually it's a stair step waveform which approximates the analog input waveform. So if we have the sample values here, so the hold operation will create a stair step or approximation of the analog input waveform. Okay? So the analog to digital conversion translates the analog signals, the real world signals, like for example, not only sounds, but we also have some analog signals like temperature, pressure, voltage, current, distance, or light intensity, and they are all converted into digital representation of that particular signal. Okay, and this digital representation can then be processed, it can be manipulated, it can be computed, transmitted, or stored. So this is a sample of a analog to digital conversion. So we have the analog signal here, and we have the circuit here to produce a digital signal output. Okay? Now, to convert a signal from continuous time to discrete time, so what do we need? Again, let's review. What do we need? We need sampling, no? So, but before sampling, we need to filter, no? To remove the distortions coming from the analog signal. And then after the sampling, we need the holding. Okay? To produce a stair step of the signal, yeah, of the analog signal. So we call it now digital signal. Okay? So this is the basic operation of an analog to digital conversion. So actually it samples an analog waveform at uniform time intervals and assigns a digital value to each sample. And the digital value appears on the converter's output in a binary coded format. So how do we compute that? So actually we're not computing that, no? The circuit computes that, no? So we have reference input and an analog input here. It goes through the circuit, okay, and it produces a digital output. Now, to compute for the digital output code, which is a binary code format, we know that in digital we only have ones and zeros, right? So we obtain that by dividing the sampled analog input voltage, okay, divided by the reference voltage, no? And then multiplying it by the number of the digital codes, no? For example, how many bits we have? For example, we have 4 bits, okay? So it's multiplied by 2 raised to 4 minus 1. So that will be the formula. So the resolution of the converter is set by the number of the binary bits in the output code. Okay? Now we have a term here called quantization. Okay? Quantization. And it's the process of converting an analog value to a code. So when we say we have an analog signal and we try to convert it to a code, we call it quantization. Okay? And in this process, the analog to digital conversion converts each sampled value of the analog signal to a binary code. So that is what we call quantization. So this is an example of how quantization works. Okay? So you can see from we have the analog signal here, okay, and we have the stair steps of the converted analog signal. It's now converted into a digital signal, okay, and you can see from here the data is held for the entire sample period here, and this quantized to the next lower level. Okay, so from the higher level it is quantized to the next lower level. Here you can see here the illustration tells us that 2 bits are required for 4 levels. So we have 4 levels here, 0 0, so we have 2 bits, 0 1, 2 1 0, and 1 1. Okay, 2 bits are required for 4 levels. Each quantization level is represented by a 2-bit code on the vertical axis. And if we try to graph the sample intervals, now for example, we have a sample intervals of 1 to 13, and these are all the quantization level, no? From the higher level to the lower level, you can see from here the codes that are generated. So for example, if we have quantization level of 2, the code will be 1 0. And if we have 1, we have 0 1. If we have 3, we have 1 1. Okay, so it's converted into a binary code. The two important ADC parameters are resolution, or we call it the number of bits, and throughput, which is the sampling rate of the analog to digital converter that can handle in units of samples per second, or SPS. So we have the resolution and the throughput. Common types of ADCs. So we have the flash or the simultaneous. We also have the dual slope, successive approximation, and sigma delta. So I think we don't have some examples of this, but you can also you can search this from the internet. Okay, these common types of analog to digital conversions. Here we have the flash or the simultaneous analog to digital converter, and this method utilizes special high-speed comparators. Okay, so you remember some linear application of the operational amplifier that we discussed last week. So we have the comparator. Okay, it compares the reference voltage with the analog input voltage. Okay, so we're actually comparing the two voltages using the comparator amplifier. Okay, so this is how the flash analog to digital converter, or the simultaneous analog to ADC converter functions. So from the example here, okay, so you can see here the operational comparators are in the middle of everything, okay, and it's connected to some inputs. These inputs are coming from the sample and hold circuit. Okay, so when the input voltage exceeds the reference voltage for a given comparator, a high is generated. So we are actually using, in this example, we are actually using a 3-bit converter which uses 7 comparator circuits. So how many op amps we have here? 7, right? So in general, 2 raised to n minus 1 comparators are required for conversion to an n-bit binary code. Okay. So we see here a voltage divider circuit, which in turn we call it the reference voltage. No? For each comparator, we need to set resistance. Okay. And then after that, after the operational amplifier comparators, they are all connected to this integrated circuit, or IC. No, we call it the encoder. Okay, and this encoder is enabled by a pulse on the enabled input. No, this one, and a 3-bit code, which is D0, D1, D2, representing the value of the input, appears on the encoder's output. So definitely this will be the output. We call it the parallel binary output. Okay? So this is what we call the flash. This is the example of the flash, or the simultaneous analog to digital converter. Okay? So let's have an example here of some computations. Actually, there's no computation here. So we are asked to determine the binary code output of the 3-bit flash below for the input signal. Okay, and the encoder enable pulses, which is shown. The reference voltage is positive 8 volts. So we have some enable pulses here from 1 to 12, and we have an analog input voltage of 0 to positive 8 voltage. So as you can see here, the signal that are generated are not typically a steady signal, no, but actually we have a stair steps of signals here, no, going up and then going down and then goes up again. A typical analog signal, no, but it's converted into a digital format. Now the solution for this is this, no, this actually we cannot do the solution, but we are actually the circuit does this, no, like if we have this particular signal, we enter it into this particular circuit, and we have the following output, the 3-bit output. Okay, we call it the 3-bit binary parallel output. So at certain levels of pulses, so we have the following values, no. For example, at impulse 2, we have a value of 100, and what is 100? That's 4, right? We call it 4 volts in terms of volts. And at period 3, we have 110, and 110 is 6. At period 4, we have 7, and then it goes down to 6 and 4 again, and then it goes to 2. At period 8, we have 0 voltage. But it is actually represented in terms of different bits here, no? In terms of D0, D1, and D2, they are represented in different ways. Okay, it's represented in terms of Just typical zeros and ones. Okay? So that's the solution to the problem number 1. Now, in terms of digital to analog conversion, this is actually the opposite, no? So if we converted an analog to digital, to be able to be understood, for example, if my voice will be converted to digital, how do you hear it? In your microphone, in your headsets, or in your speakers. It is also converted back to the analog. So we have the digital to analog conversion, where the digital data that has been processed will be converted back to analog. And we have two methods of digital to analog conversion. We have the binary weighted input, and we have the R2R ladder. Okay? So you can see here a circuit of an operational amplifier. This is an operational amplifier, and the inverting input is connected to a values, no, certain resistors, no, and these resistors, the values of the input resistor here that you can see, no, as you can see that the value is doubled, no. Here we have the R, and this one is twice the R, and then this one is twice the second one, and this one is twice the third one. Okay, so definitely these are all voltages, no, these are all input voltages coming in to the inverting input of the amplifier, but they are all connected to resistance or resistors, no. And the values of the input resistors are chosen to be inversely proportional to the binary weights of the corresponding input bits. You can see here, if the input bits is 2 raised to 0, no, that will be the opposite of the corresponding input bits. So you see here, the larger the input bits is, the lower the resistor. But the least bit that we have here is 1, right? 2 raised to 0 is 1. Or, yeah, okay? So we have the maximum resistance here. Now, to compute for the value of the current, we have the voltage over the R. Okay, so we have the current in this particular input is computed as the input voltage divided by 8 times R. And then this one, for the current I1, that is voltage over 4R. And then I2 is equal to voltage over 2R. And then I3 is equal to voltage over R. Alright? Now, the output voltage can be computed as the final current here and the final resistance. Okay? So that will be the output voltage. Now, the number of different resistor values and the voltage level, which must be exactly the same for all inputs, are the disadvantages of this ADC. For example, in this case, the lowest value resistor here corresponds to the highest binary weighted input of 2 raised to 3. No? I mentioned this already. But the output voltage is proportional to the sum of the binary weights. Okay? Because the sum of the input currents is through the final resistor here. Okay? So as a problem, we are asked to determine the output of the DAC in figure below. This figure. If the waveforms representing a sequence of 4 bits in figure are applied to the inputs, input D0 is the least significant bit. Okay, so the least the bit the higher the resistance, no? And the higher the number of bits, the lower the resistance. So here we have resistances of 25 kilo ohms, 50 kilo ohms, 100 kilo ohms, and 200. So it's actually doubling, no? So they are all connected to the inverting input, and we have the final resistor here of 10 kilo ohms, no? So basically the illustration of the signal are given here. We have some impulses here of 0 to 15. Okay. So we are asked to compute for the output, no? Output voltage. So let's try to compute that by computing first the current. Because we need the formula for the output voltage, we need to compute to the output voltage is equal to the final input, final current, and the final resistance. So before we do that, we need to compute first for the current, no? So these are all the currents that were produced. So we have an input of 5 volts in I0, and we have a resistance of a very high resistance of 200 kilo ohms. So definitely we have 0.025 milliampere. So the higher the resistance, the lower the current, and the lower the resistance, the higher the current is. But it's not so much, no? You can see here they are all converted into negative, no? Because they are connected to the inverting input. So all the voltages that are produced are all negative. Okay? So these are all some simple calculations now. I think we have some examples of this in your assignment. Very easy. Now, performance characteristics of ADC are the following, no? We have the resolution. We mentioned this a while ago. And it is the reciprocal of the number of discrete steps in the output, dependent on the number of input bits. For example, we have a 4-bit digital to analog conversion resolution. So how do we compute that? That will be the reciprocal of the number of discrete steps in the output. So that basically is 1 over 2 raised to n, which is 4. 2 raised to 4 is 16 minus 1. That's 1 over 15 multiplied by 100. So the resolution will be 6.67%. Okay? So that's the resolution concept. So this is one of the example of the performance characteristics of the ADC. So if you want to compute for the resolution, which is the reciprocal of the number of discrete steps in the output, so this is the formula, no? So that will be equal to 1 over 2 raised to n minus 1 multiplied by the 100, no? To take into account the percentage of the resolution. Now the next thing, another performance characteristics is what we call the accuracy. Now, how do we get the accuracy of the ADC? So it's derived from a comparison of the actual output of a DAC with the expected output. Okay? And it's expressed as percentage of a full scale or maximum output voltage. Ideally, the accuracy should be no worse than the plus minus half of at least the of a least significant bit. Okay? So as an example, we have here a converter full scale output of 10 volts, and the accuracy is equal to plus minus 0.1%. So the maximum error for any voltage can be computed as 0.001 multiplied by the 10 volts. So that will be equal to 10 millivolts. So that means an 8-bit converter the least significant bit is 0.39% of a full scale. So the accuracy should be approximately plus minus 0.2%. Okay, that's how we compute for the accuracy. Another performance characteristics. So I would like to correct this. So this one is not ADC but DAC. No, we're talking about ano here, no? Not analog to digital converter, but we're talking about digital to analog converter. Okay, so forgive me for my mistake here. So this should be DAC. So in terms of linearity, a linear error is a deviation from the ideal straight line output of the DAC. So there is also a special case called the offset error, which is the amount of output voltage when the input bits are all zeros. Alright? So we have that. Another performance characteristics of DAC is, we call it the monotonicity. Okay? It's difficult to... so it's coming from the monotonic. So DAC is monotonic if it does not take any reverse steps when it is sequenced over its entire range of input bits. Alright? Finally, we have the settling time. Okay? And that is the time it takes DAC to settle within the plus minus half of the least significant bit of its final value when a change occurs in the input code. Okay? I think this is the last example that you will see. Okay? So we are asked to determine the resolution and express it as a percentage. So for the following examples, no? So we have here an 8-bit DAC and a 12-bit DAC. So how do we compute for that? So we compute for that using the formula 1 over 2 raised to n minus 1 multiplied by 100. So we will obtain percentage value. So that will be equal to 2 raised to 8 is 256. No, minus 1, that will be 255. And 2 raised to 12 is 4096. So minus 1, that will be 4095. So the percentage are the following. So you can see here the resolution of the DAC is higher when we have fewer number of bits. Okay? The higher number of bits we have, the lesser is the resolution. Okay? So all of the references that you will see, that you saw, are all coming from this book. No? Okay? So I think this is the end of this topic.